In this concluding database design unit, we bring together a number of advanced aspects of database application design. It begins by extending the coverage of data normalization in an earlier unit, describing Boyce-Cobb normal form, which is a refinement of the original third normal form, and provides a different view of how to generate a set of relations in third normal form. The unit then covers a number of important issues to be considered when decomposing relations during the process of normalization. The following is a brief summary of the first three normal forms. 1. NF. Identify the determinants of data items, and through the removal of any repeating groups arrange the data items into an initial first normal form relation. 2. NF. Remove part key dependencies from the relations in first normal form, that is, for non-key. 3. NF. Remove any transitive, indirect dependencies from the set of relations in second. Third normal form. Remove any transitive, indirect dependencies from the set of relations in second normal form relations to produce a set of relations where all attributes are directly dependent on the primary key. A relation is in Boyce-Cobb normal form if all attributes which are determinants are also candidate keys. Boyce-Cobb normal form is stronger than third normal form and is sometimes known as strong third normal form. Transformation into Boyce-Cobb normal form deals with the problem of overlapping keys. An indirect dependency is resolved by creating a new relation for each entity. These new relations contain the transitively dependent attributes together with the primary key. Fourth normal form, 4 NF. A relation is in fourth normal form if there are no multi-value dependencies between the attributes. Multi-valued dependencies occur where there are a number of attributes that depend only on the primary key, but they exist independently of each other. This entity relationship diagram represents the following. Each performer may have many bookings, so the relationship between performer and booking is one-to-many. A performer earns a fee, the value of which depends on the performer type, so the relationship between performer and fee is 1-to-1. A performer can only be of one type. An agent may make a number of bookings, so the relationship between agent and booking is 1-to-many. Any venue may have been booked several times, which makes the relationship between venue and booking 1-to-many. Each event may be involved in a number of bookings, so this relationship is also 1-to-many. The relationships that exist between performers, agents, venues, and events are shown by their connections through the bookings. The process of denormalization consists of reversing, or, in the case of a new application, not carrying out in the first place the steps to fully normalize an application. Whether this is appropriate for any given application depends critically on two factors. Whether the size of the application is sufficient that it will run slowly on the hardware or software platform being used. Whether failing to carry out certain steps in the normalization process will compromise the requirements of the application's users. Over-normalization. A further technique for improving the performance response of database applications is that of over-normalization. This technique is so called because it results in a further decomposition of the relations of an application, but for different reasons than that of the usual normalization process. There are essentially two approaches to over-normalization of a table. We can divide it up either horizontally or vertically. Example of over-normalization. Splitting a large table into a number of smaller tables often reduces the number of rows or columns that need to be scanned by specific query or update transactions for an application. The smaller tables retrieved by queries restricted to one, or even a few, of a number of partitions will take up less space in main memory than the large number of rows fetched by a query on a large table.